Tony, for inviting me to give this talk, and thank you all for being here. So I'm going to talk about the rank function of the rigidity matroid. And I'll go through some more generalities about matroids in order to do this, and sort of the kind of like guiding results for this talk come from a paper of Lovash and Yemeni in 1981. So I would still like recommend actually going through the paper because I'm not really going to get through a lot of the proofs or really any of the proofs. Here, I'm going to send a link to the paper in the chat. I guess the point of this talk is to sort of like give you sort of the background around that paper in a very like general kind of like Metroid theoretic sense. So to begin, I just want to start with rank functions of Metroids. So let M be a matroid and define the function R that's going to go from the subsets of your ground set E to the integers. And we're going to define this by the rank of some set S is equal to the maximum over independent sets that are contained in S, and we'll take its cardinality. So yeah, and I don't know what yes, I apologize in advance if my notation is maybe not consistent with what Tony's been doing, but I'll use this notation M, E, I for a matroid, where M is the matroid, E is the ground set, and I is the set of independent sets. But anyway, the rank function, it just takes a subset of your ground set and spits out the size of the maximum or the largest independent set within it. So for example, if M is the matroid of linear independence, of a matrix with column set E, then the rank of some subset of columns S is the rank of the column submatrix of A on column set S. Oh, by the way, is this recording, has record been hit?
Yes.
Okay. Just making sure. All right, cool. And then another example that's going to be relevant for here comes from graphic matroids. So let's say recall that given a graph G with vertex set V and edge set E, the graphic matroid M of G has ground set E, the edges of G, and independent sets are cycle-free sets of edges. The rank function is given as follows. The rank of a subset S is equal to the number of vertices in the entire graph minus the number of connected components of the graph V with edge set S. Okay. So just since this is going to be important later, I'll give an example of this example. If G is, say, the complete graph on 4 vertices, and we'll say S is this, then the rank of S is number of vertices minus the number of connected components, which is 1, which is 3. And if, say, S prime is just 2 edges, then rank of S prime is 4 minus the number of connected components, which is 2, which is 2. Okay. All right. So, yeah, and by the way, feel free to stop me at any point with questions. So anyway, it turns out there's a very nice characterization of which functions can be rank functions of matroids. So here's a proposition.
Hey, Daniel.
Yes.
Can I ask about the previous example?
Yeah, please.
So each connected component will give a vector in the kernel of the incidence matrix of the graph, right?
Yes. Or not quite. So over
sort of the delta vector on that connected component will be a linear independent vector in the kernel of the incidence matrix.
yeah. So not quite. Okay. So if your incidence matrix is over the field with 2 elements, then yes. But if not, you have to put an orientation on the edges, any orientation, and then take the like directed incidence matrix, and then that will be true.
Right. Okay. That's the one I was thinking of. Then can you
Okay.
help
Okay.
me? Can you help me? Is this easy to see then immediately?
That the rank function. So let's see.
Because the cycles are the vectors in the kernel of the transpose.
Okay, the way to think about this, I would say, is each connected component has a spanning tree.
Okay.
And if you just take a tree and look at that incidence matrix, there's not going to be any linear dependencies.
Yeah.
And as soon as you have a cycle, that gives you a linear dependence. So
Okay. That was better.
okay.
That's a better way. Okay, thank you.
Yeah, no problem. Any other questions? Okay. So rank functions of matroids can be characterized. And in fact, you can define a matroid in terms of its rank function instead of in terms of its independent sets. And here's how. So, whoops.
Okay. Hey, Daniel, sorry. Can you finish? I think I cut you off because the rank function is what I wanted to see if you can see that easily. If we scroll up a little bit, the rank function is number of vertices minus connecting components. And can you finish explaining?
Right. Okay. So each connected component of the graph is going to contribute. Okay. So imagine your graph is just a forest, right? Now the forests are independent sets, and in particular, each connected component of the forest is an independent set. So the rank of each tree in a forest is just the number of edges, and the number of edges is just the number of vertices in that connected component minus 1 because it's a tree.
Oh, that's okay. That's good.
Yeah, so now do this over all connected components. What you're doing is you're adding up the number of vertices in each connected component, which could be an isolated vertex, and then subtracting 1 for each connected component.
Okay, thank you.
Okay, yeah, and that's it for forests. And then for graphs that aren't forests, well, just restrict to a spanning forest. And that's the best. That's the largest independent subset that you can make.
Okay, perfect. Thank you.
Yeah, no problem. All right, so here's what a rank function of a matroid is. So let E be a set then a function R from the subsets of E to the integers is the rank function of a matroid. If and only if it satisfies the following three axioms. R1, which is just that R of S is always greater than or equal to 0 for all subsets. R2, which is that the rank of some set is less than or equal to the rank of some set union a new element, which is less than or equal to the rank of S plus 1 for all subsets S of E and elements X in E. And then finally, so with any sort of axiomization of matroids, you usually have a handful of kind of like easy axioms and then one little more subtle one. This is the more subtle one. And it says that R is submodular, which means the following. It means that the rank of S, union T plus the rank of S intersect T is less than or equal to the rank of S plus the rank of T. And of course, this is for all subsets S and T of E. Okay. And now just two quick notes. If R is a set function, is the rank function of a matroid M, then independent sets are sets such that their cardinality is equal to their rank. So yeah, that's like the first note. And then the second note is that rank functions are monotone. In other words, the rank of A is less than or equal to the rank of B whenever A is a subset of B.
Hey, Daniel,
Yes.
is there sort of like an illustrative example for the submodular condition?
So define your matroid, your rank function, to just be the cardinality of a set. So then you get an equality here in this submodular inequality, right? The cardinality of S and T, yeah, so S union T plus the cardinality of the intersection is equal to the cardinality of S plus the cardinality of T. This is just inclusion exclusion, right?
Yep.
So now the rank function is telling you that, well, when you take, so yeah, I'm gonna phrase that just maybe it's a little bit more illustrative to see this as follows. So I'm not exactly answering your question. I'm just sort of, okay.
This is definitely helpful already.
Okay. Oh, okay, good. So what the submodular function is saying is that, well, by taking the union of two things, you're not going to increase the rank any more than you would just by like adding things in. Like, in other words, like, the whole is not more than the sum of the parts. That's kind of the that's sort of how I think about it intuitively.
But there can be surprising inequality where it drops.
Yeah, like you can have redundancy, right? So for example, like now let's say you have a matrix Let's do a really dumb example. We'll call this 1, 2, 3. So the rank of the set just consisting of 1 is equal to 1, and the rank of the set 2 and 3 is equal to 2. And now the rank of the union of these two is strictly less than the rank of 1 plus the rank of 2 and 3 plus the rank of the empty set, which is 0. And basically what this means on an intuitive level, or like in this example, is that you're not going to increase the rank or the dimension of the linear space spanned by these vectors by throwing in this redundant thing. So the submodular inequality basically says that as you add more stuff, you can get redundancy, but you can't get like synergy.
This is great. Okay, now this third one makes complete sense. Very natural. Thank you.
Great. I'm glad to hear that. Yeah, any other questions, by the way? All right, so now what I want to do is I want to weaken these axioms. So suppose f is a different set function. Satisfying these three axioms. So I'm going to call the first one R prime of 1, which is that f of s is greater than or equal to 0 for all non-empty s. R prime 2 is going to be that f is monotone. So in other words, f of a is less than or equal to f of b if a is a subset of b. And then R3, no prime there. This is just f is submodular.
How did these change? What were the unprimed ones?
Yeah, so the unprimed said that it's non-negative always. Now I'm allowing f to be negative at the empty set. The second one used to be this, which said that your rank can increase by at most 1. Sorry, this. Your rank can increase by at most 1 when you add a new element. Now all I'm saying is it just has to be a monotone function. And then the third axiom is the same. It's just submodular. So we're going to consider these. I'm going to get to why real quick, but just so the natural example to keep in mind is let E be a set of linear subspaces of f to the n for some field, and then define f as the set function by f of s to be equal to the dimension of the span of the union of all the elements in S. Then I claim that f actually satisfies these three axioms, but it's not the rank function of a matroid, because in particular, if say, you have something in E that's like a two-dimensional subspace, well then f of that can be 2, and the rank of a single element in a matroid is never going to be more than 1. And that follows from the original unprimed R2 axiom. And sort of the example that I actually that motivates considering this at all is
Wait, I'm sorry, Daniel. Could you just say that example again? The two.
Yeah. So E consists of subspaces of a ambient vector space.
Oh, it's subspace,
But
so it could be a two-dimensional space itself.
yes,
Okay. Yes. Okay. Thank you.
yeah,
That
yeah.
makes sense.
Sorry, could you also, I think I missed what you said when you defined QS. Is that the span of the union of all elements of S?
Yes.
Thanks.
Yeah, and so and just real quick to sort of like bring this back down to earth a little bit more, when all of these subspaces have dimension 1, this is just a matroid. Yeah, but then another, so yeah, another example that is going to be more relevant for rigidity is I'm going to get to this in a second. Let R1 and R2 be rank functions of matroids on the same ground set. Then F, which is equal to R1 plus R2 minus 1, satisfies the above. And in particular, this is why I actually need the flexibility to be negative on the empty set, because note that, well, with this example, F of the empty set is going to be negative 1. And then finally, just another, if you've studied Metroid theory before. Oh, sorry. Actually, no. Forget that first. No, sorry. We're going to come back to that. Yeah. So okay. These are the class of functions that I want to consider, and the reason why I'm introducing them is the following theorem of Edmonds and Rhoda in 1966, which says that if F is a set function satisfying these 3 axioms, R prime 1, R prime 2, and R3, then let I be the subsets of E satisfying that the cardinality of I, subsets of E satisfying, I need to name these something. Sorry, the subsets I of E satisfying for all subsets I prime of I, the cardinality of I prime is less than or equal to F of I prime. Then M, which I'm going to define to be the matroid on ground set E with independent sets I, is a matroid. And I'm going to denote it by M of F. Now there's more. So moreover, the rank function of M of F is the following. It's the minimum over
Daniel,
F. Yeah.
I'm sorry. I don't understand this definition. Is script I the maximal collection of subsets or something like that? I mean, this doesn't define a unique, doesn't look to me like it defines a unique object.
So, okay, so I guess here I'll make this. There's 2 I's here. There's a script I, and then a block I.
Yeah.
So script I is a set of sets.
Yep.
And block I is in script I if and only if it satisfies this property.
Um, okay, no, I don't understand this at all. Can you read that property to me? I'm having trouble even reading it. It's block I prime is a
Yes.
subset of I.
For all subsets I prime of I, the cardinality of I prime is less than or equal to F of I prime.
Ah.
So that's the test whether block I is in script I.
Yes.
Okay, now I understand. Yes, this makes sense. Okay, thank you.
And actually, I'm glad you asked that because I realized I forgot to mention I prime not empty. This might not be true for the empty set, but that's fine.
And then Daniel, can I ask, like, is there an is there an example where f of I prime is bigger, strictly bigger than the number? Is that going to be the same subspace example?
Yeah, actually. So take the subspace example with let E be a set with one element that is a subspace of dimension 50, say. Then you define a matroid on that set with one element where your independent sets are any subset of this one element set whose cardinality is less than F of that value. So now F of the empty set, empty set's always independent, whatever. Take your unique non-empty set consisting of that one element. The cardinality of that is 1, and F of that 50-dimensional subspace is 50, and 1 is less than 50. So that's an independent set.
So can I think, if before I thought matroids were columns of a matrix, aka one-dimensional subspaces of a vector space, now I can think that matroids also have subspaces.
Yeah, I guess. I mean, like flat. So yeah, if you have a matroid, you can group together, like you can partition the elements of it. You have to be a little bit careful. And I that might take us a little bit too far down a rabbit hole to like be precise about what I mean there. But like, if you take like some set of flats of a, actually, I have to think about this a little more. But yes, there is a way to go from like, there is a way to like combinatorially abstract this example of subspaces.
Okay, and then can I ask another question?
Sure.
Okay, so if we take E to be some set of subspaces, and we define F as you did above with like the dimension of the span of the union, then by this we get a matroid. But can you give another example of a set E and a function F where this works?
Yeah, and we're getting there. That's actually the 2D rigidity matroid.
What's the set E and what's the function F?
We'll get there.
Okay.
Stay tuned. Yeah. So,
is there a third example that we won't get to?
There's plenty of examples. Because this is something that appears in like combinatorial optimization textbooks, but I only care about the rigidity theory example. Sorry. No, there are other examples. In symmetry force rigidity, I have a paper on this. We can talk about that later. But yes, there are other examples.
Okay.
And there's even motivation outside of rigidity theory.
Just like one phrase of the function in that case?
One phrase of the function?
One phrase to describe this function, even though you can't obviously talk about it.
So we'll get there. Let's talk about that later. There's too many things to define to do that without just being confusing.
Okay, fair enough.
I will give you a concrete. The 2D rigidity matroid is an example of this, and the function is not that difficult. We'll get there. But before, let me the rank function of matroids of this form. I'm going to write it down. I'm going to write it down and then I'm going to explain it. And it's complicated for humans, but polynomial time for computers. So the rank function is this, where the minimum f is, or sorry, the minimum is taken over partitions f equals f0, comma, dot, 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 comma, fk of your ground set. So I don't want to dwell too much on this exact, like what exactly this, too much on this rank function. The point is that this can be computed in polynomial time.
But the rank function should take in a subset of E and spit out a number. What's the subset?
Oh, sorry. Subset of, yeah, good point. Yeah, so here, the rank of S is equal to, yeah, sorry, that's a good point.
Okay, thank you.
Yeah, this can be computed in polynomial time, and this is due to a result of Quatschl, Lovash, and Schreiber, 1981. And it actually uses like linear programming in the ellipsoid algorithm. So it's polynomial time, but slow. But anyway, okay, okay, now here's where I get to the punchline and the question that you asked, Alex, is here's an example, and this is due to Lovash and Yemeni, 1982, which says that, let R, or sorry, no, let E be the edge set of the complete graph on n vertices, Kn, and then let R from 2 to the E to the integers be the rank function of the graphic matroid of Kn. Then the 2D rigidity matroid in other words, the matroid whose bases are these 2-3 sparse graphs or 2-3 tight graphs. Then the 2D rigidity matroid is M of 2R minus 1. So in other words, well, I'll give you a minute to just process that, and then I'll do an example.
So the function f is equal to the function twice of the function r minus 1?
Yes.
Okay. And then in the definition above, there was a sum, and it just wasn't clear to me that this is like well-defined. Like, what singles out f naught, that we're taking the cardinality of f naught, but then we're applying f to the f sub i's?
So, I mean, this is, you're taking a minimum here. So curly f, this consists of a choice of f naught and then a choice of all the others. F naught you're taking the cardinality of, the rest of them you're taking f of, and you're adding them up. And there are many, many ways to do this. And the minimum number that you get out is the rank of S.
I see. Okay. So which one is f naught can also be there. We just take the minimum.
Yeah, yeah.
Just one of them you have to actually count. That's all.
Yeah, yeah.
Okay.
And just one. I mean, and this is something that you can compute with linear programming, which can be solved in polynomial time with the ellipsoid method. And yeah. And actually, another thing that's maybe another computational consequence is that this gives you a polynomial time certificate that your rank is less than or equal to some number, right? Because if you exhibit some partition such that, if you, forgetting about the minimum, this thing evaluates to like 12 on it, then you know that the rank of your Metroid, your set is at most 12. That's the other sort of like consequence of this. But anyway, okay, yeah, anyway, the whole punchline is now that the 2D rigidity matroid satisfies this, or it can be constructed this way. And a consequence is that you have this formula for the rank function that can be computed in polynomial time. So yeah, I guess the corollary here is that the rank function of the 2D matroid is given by 2D rigidity matroid. Is given by the rank of some graph G is equal to the minimum over all ways of partitioning it of the edges, F0 plus the sum of twice the number of vertices in Fi minus 3.
Wait, but we have a 2R minus 1. Now we have a 2 something minus 3.
So what's the rank function of the complete graph, right? So R, sorry, I'm gonna R is overloaded here. Let's make this R hat. Right, remember R is the rank function of the graphic matroid, and we already established that R of G is just equal to, oh, I'm sorry, 3 shouldn't be here. This should be number of connected components of Fi. But it turns out that if you just restrict these partitions to be into connected graphs, that's okay. So that's why I put a 3 there. But yeah, just remember that the rank function of G is equal to the number of vertices of G minus the number of connected components of G. So this should actually be, sorry, I'm sorry. This is, this should be twice this minus, sorry, twice this minus 1.
Hi, Daniel. I have a question.
Yes.
So when you say this rank function can be computed by the ellipsoid method, so this ellipsoid is a polynomial in terms of data length L, right?
Sorry, what was that? Polynomial in terms of what?
So the ellipsoid method is bounded by a polynomial. And this polynomial is in terms of the data length L, right?
In terms of the what, L?
The data length.
Data length, okay, yeah.
The size of your data, right? So what's this data length corresponding to your graph, or how do you decide this?
I don't know off the top of my head, but yeah, I mean, if you're interested, you can check the paper of these 3 authors. But yeah,
okay,
I mean, it's polynomial. The length of the data is polynomial in the number of, say, vertices. So.
So somehow you take this computation over all partitions and you turn it into a linear program in some dimension, and that dimension is the length of the data?
No, the length of the data is the entry, the length of the entry. So yeah, like for example, you have 1, 1, 1, 1. This data length is 4, right? This is a.
So yeah, I don't want to go too far afield into implementation details, just since I don't really know much about that, and honestly, if you were going to do this practically, you wouldn't even use the ellipsoid method, right? Because simplex method is faster, right? Or whatever people who work in optimization do is faster than the ellipsoid method. So the point is the point is that you can do this. How you would practically implement that is maybe for another course. But yeah. But anyway,
yeah. Okay. Thanks.
Okay, but yeah. So okay. This is the whole punchline. Yeah, and just to sort of see this in an example. Oh yeah, and I guess by the way, so I mentioned rank functions of Metroids. Why you should care? So the rank function of a rigidity matroid tells you, oops, the minimum number of edges to add to a graph in order to make it rigid. And in particular, this number for n vertices is 2n minus 3 minus the rank of your graph. And so, for example,
so you're not saying that it's the rank itself.
It's not the rank itself. It's like
okay, yeah.
The co-rank, I guess.
Rank function helps you determine.
Yeah. And I guess, you know, if you want to think about it intuitively like itself more directly, it's like the dimension of your linear space of infinitesimal flexes.
Mm-hmm.
Or sorry, no. That's no. It's the that doesn't solve the problem. It's like the codimension of that. Wait, no. Yeah. Sorry. This number is the this co-rank is the dimension of the linear space of infinitesimal flexes.
Hi, Daniel. Is this statement true for other dimensions, or is this only 2D?
It's only 2D.
Oh, well, obviously with different values, but is there
even with different values, it's only true 2D. Yeah, and there's a geometric reason for this actually, which I can I'll briefly say something about that actually. So like, and I'm probably I hope I don't lose people, but it's possible that I will. If I do lose you, just ask me to slow down. But the geometric reason for this, why it doesn't generalize, is that so the rigidity matroid is the linear matroid of the tangent space to the manifold parameterized as the manifold in, let's say, R to the n choose 2 parameterized as like dij is equal to xi minus xj squared plus yi minus yj squared, which is just, you know, the distance between xi and xj squared. Okay, and you know, I'll just say like forget non-smooth stuff. I'm being a little hand wavy here.
And on your right hand side, you should maybe say V or something.
Right hand side.
The norm squared of xi minus xj that you've written.
VI minus VJ, maybe.
Oh
Yeah.
Yeah, thanks. Yeah. Okay. And now, so there's two claims here. So one, I can expand and work over C. So I just let X, Y, and their values be complex and just keep the same polynomial. Two, in this case, this manifold is a Hadamard product, which I haven't defined, of two linear spaces whose bases actually two linear spaces. Sorry, I'm gonna just say such that if A is a basis, the matroid of A transpose is the graphic matroid of Kn. And then three, if a manifold.
Daniel, you said to stop you, so.
Yeah, please, yeah.
Of course, I haven't been shy before. Okay, so A is a basis of one of the linear spaces?
Yes.
Or what?
Oh, so okay. So okay, yeah. They're okay. They're two linear spaces. They each have they're different. But if you take a basis of either of them and then transpose it, and then look at the matroid, in both cases you get the same matroid, which is the graphic matroid of the complete graph.
Okay, and then another question.
Yeah.
This is a manifold. It doesn't have any singular points.
I'm waving my hands here. Forget about the singular points. It's not, but
Okay.
it's no, it's not. But yeah, see, yeah. Forget I here's my little parenthetical. Forget non-smooth.
Oh, forget. I thought it said to get.
Oh no, sorry.
Doesn't make sense. So
Forget non-smooth stuff, yeah. It's a variety, it's not a manifold. But anyway, yeah, and then sort of like the general big guns here, which is actually goes back to your original question, Alex, of how do you get more stuff defined like this? If a manifold is a Hadamard product of linear spaces, let's say with bases, let's say A and B, then the matroid of the tangent space is actually given by this matroid that you get from summing the rank function of A, of the matroid of A transpose, plus the rank function of the matroid of B transpose minus 1. And now here's where it breaks down in 3 dimensions. In 3 dimensions, you're not a Hadamard. The relevant manifold here is not a Hadamard product of two linear spaces. So I
And
think
where can we read more about this story that you were just outlining?
yeah, this story is a paper of mine, actually. I'll put that up. I'll pull up an archive link. Oh, and the proof uses tropical geometry, actually. So you would like that, Alex. Yeah. Yeah, I hope I didn't lose too many people there. I know the details are like, I really waved my hands at the details there, but hopefully that gives a little bit of clarity as to why such a thing like you wouldn't expect such a thing to work for 3 dimensions. Yeah, and then finally, I think to most people in rigidity theory, the point of the paper is actually the following, which I did not get to, which says that this is a corollary of Lovász, or corollary is maybe not the right word, but a consequence of Lovász and Yamini's characterization here, which they go through in their paper, is that if G is 12 connected, then not 12 connected, sorry, that's the wrong number. 6 connected, sorry. If G is 6 connected, then it's rigid in 2D. And they use this characterization of the rigidity matroid, in terms of these rank function, these non-rank submodular functions in order to get that. You can read about that in the paper. It's not a very long proof. And there's a conjecture that comes out of that is if G is 12 connected, then it's rigid in 3D.
Dan, just remind me what 6 connected is. Does that mean that if you remove any 6 vertices, you're still connected?
It means that if you remove any 5 vertices, you're still connected.
5, okay. You need to remove 6 in order to disconnect it.
Yes,
okay.
Exactly. You need to remove at least 6. So I actually was able to get through everything I wanted. So yeah. Are there any other questions in the last 5 minutes?
I'm just...
Yes. So yeah. So this back to my my question about the rank function. So this rank function can be computed in polynomial time in terms of number of edges and the number of vertices.
Mm-hmm.
Is this true?
Yes.
So this. Okay. So so given the So given the graph, then this polynomial is totally determined by the number of edges and the number of vertices of this graph, the complexity, right?
Yeah.
Okay, yeah, thank you.
This conjecture in 3 dimensions seems very odd to me. Is there any computational evidence for that, or like, it's a very odd statement. I would have expected that you can construct examples with arbitrarily high connectivity.
It's actually,
they're not rigid.
Yeah, actually, Tony, do you want to take this one? This is probably more.
Yeah, sure. So Lovaas and Yemeni construct an example that is 11 connected but not 12 connected, that is not rigid. But you can go the other way. So you could replace the number 12 with whatever your favorite big number is, and it's still a conjecture rather than something we can do. So you seem to have the opposite intuition to me, Will. My intuition is that it should, if you make the 12 a really big number, it should be easy to prove it's rigid, because the 100 connected says minimum degree is 100, and a minimally rigid graph in 3D will have average degree 6. So you've got so many extra edges compared to the minimally rigid subgraph that it should be easy to show the rank is high with all those extra bits. But somehow it's not.
So Tony, is it true that 12 connected is rigid in the abstract maximum Metroid?
Yes, so Bill Jackson, Katie Clinch, and Shinichi Tanigawa's recent papers prove that, yes, in the cofactor Metroid, so the maximal three-dimensional rigidity Metroid, this conjecture is true.
Yeah.
With the conjecture, what's the current stumbling block on proving it? Or is it we don't know how to tackle it?
So, well, yeah, I just don't know what technique to use. So you could, as I say, you could increase the number 12 as high as you want, but you need to have some reason why the rank of the rigidity matrix should be full. And I guess we don't. The reason it's true in 2D, as Daniel said, is because we know combinatorially what the rank function is in 2D, but in 3D, I think you need some geometric insight to move from this 12 connected to rank of the rigidity matrix. I don't think that's a good answer to your question, Joe, but I don't have a good answer.
Yeah, it sort of answers that we don't know how to go about it. So, yeah.
Is it just then that 12 is the lowest number that we haven't constructed a counterexample for? Or I didn't quite follow the whole thing, so you might have said it and I just missed it.
Yes, so Lovaas and Yemeni, in their paper where they proved 6 connected, they constructed 5 connected but not rigid graphs in 2D, and then they showed also 11 connected but not 12 connected graphs that are flexible in 3D. I think if you look in their paper that Daniel linked, it's sort of small complete graphs in a ring, and they're just pasted together in a clever way. So 12 is definitely best possible if it's true, and I guess 40 odd years later, if 12 was not going to be the right number, and there was a small counterexample, it would have been found. So any counterexample must somehow be quite big.
Okay, so it doesn't follow, or it's not suggested by what Daniel was saying beforehand. That, in the same way that G being 6 connected means it's rigid in 2D is a consequence of what you've just said up there. G being the conjecture that G being 12 connected doesn't seem to follow from that argument.
No, so we don't have the rank function for the 3D rigidity Metroid, and so the rank function that Daniel described was I guess the main reason why 6 connected is provable.
Oh yeah, I didn't think of that. Thank you.
Is there any conjectures for higher dimensions?
So 6 and 12 is d times d plus 1. So you could make the natural conjecture. I have no memory of reading anyone showing counterexamples or showing that was tight in all dimensions, but maybe this is in the literature somewhere, I don't know.
Also, is it known for stuff like body bar frameworks?
It's true for 3D body bar frameworks.
It is true.
I guess there is probably an analogy for d dimensions in that context. Yeah, that may exist somewhere.
Okay.
Is there something for six connected, like equivalent on surfaces?
Yes. So say on the cylinder, so if you fix a cylinder in 3-dimensional space and you ask about rigidity with the points constrained to the surface, then analog of the 2v minus 3 count is 2v minus 2, but 2v minus 2 is really nice in combinatorial. So it's 2 edge disjoint spanning trees. And so if your graph is 4 edge connected, I think it always contains 2 edge disjoint spanning trees. So you could replace 6 connected with 4 edge connected. Hence, so 4 connected always implies 4 edge connected. So that would be an easy consequence of the rigidity characterizations in that context. So somehow there, I think the rigidity characterizations are harder, but this sort of connectivity corollary is easier. You can move to a different surface and probably you can play a similar game, but not off the top of my head, I can't remember what happens for, say, a 2v minus 1 or a 2v minus 0 count.
For d equals 1, the statement is, what's the statement? If G is 1 connected, then it's rigid. And
so a graph is rigid if and only if it's connected in one dimension.
And yes,
so 1 connected means connected. So
1 connected means connected, but then the number breaks, the pattern's breaking down,
yes.
Right?
That doesn't fit the DD plus 1, but I think DD plus 1 is where the 12 is a natural in the proof technique of Lovász-Jemeny.
So I mean, the 6 connected actually gives you a lot more than just rigid. It also gives you globally rigid.
Yes.
And 2 connected is the one for globally rigid.
That's true. Yeah.
So it doesn't exactly break down. It just
interesting.
Yeah.
Okay.
It's proving something slightly different.
Yeah, and you can even go even further. So Bill Jackson and Cheapboard Jordan showed that 6 connected implies globally rigid, but they could even delete a few edges. So the 6 connected compared to 5 connected is tight, but 6 connected is not tight in the sense that you can delete a few edges away and still have the nice rigidity properties.
Is it like 2 or 3 edges or something? You can
it's something small.
Yeah.